So for the other set of past year paper I did, it is paper 51 of May June 2023 series. So this one is an even more recent past year paper with no change in syllabus. So you might expect like whatever that will come up for prelims or your actual exam to be roughly similar to this. And yeah, okay, let's begin. Alright, so for this question, they're asking about partition coefficient. So let's read the question. The partition coefficient, KPC, shows the distribution of a solute between two immiscible solvents. KPC is determined by measuring the concentration of the solute in each solvent. The organic solvent, ethoxyethane, and water are immiscible, so they cannot mix. The student is asked to find KPC of butadenoic acid between ethoxyethane and water. The expression for KPC when butadenoic acid is in equilibrium between ethoxyethane and water is shown. So again, this equation might be useful for later on if they ask us to find the expression, the KPC later on. Most likely they will. Alright, next, we're given the density of ethoxyethane and water. So as you can see, water is more dense. So usually that means that water would be at the bottom layer and your ethoxyethane would be at the top layer because it has lower density. And that would also be the answer to question AI. Alright, okay, step 1. Add 30 centimeter cube of distilled water into a separating funnel. Weigh by difference 2.81 grams of butadenoic acid into the separating funnel. Step 3. Stopper the separating funnel and shake it until the butadenoic acid has dissolved. Step 4. Remove the stopper and add 30 centimeter cubes of ethoxyethane to the separating funnel. Step 5. Replace the stopper and shake the separating funnel gently. And step 6. Place the separating funnel into a clamp. Allow all liquids to settle so that the two layers can be seen. Again, time is needed for the two layers to completely settle. That's why you clamp it. So yeah, you don't have to hold it like forever. Alright. Step 7. Remove the stopper and open the separating funnel tab to allow the lower layer, so this is your aqueous layer or the water layer, to run into beaker labeled A, and run the upper layer, which would be your ethoxyethane, into a beaker labeled B. Transfer 10 centimeter cubes of the aqueous layer into a conical flask, and you perform titration for both the aqueous layer and ethoxyethane layer. So you titrate it with 0.5 mole of NaOH. They will likely ask about concentration again. Yeah. Alright, okay. So again, for your beaker A, that would be your water, and for beaker B, that would be your ethoxyethane. And yeah. Alright. Question AI. State whether beaker A in step 7 contains the aqueous layer or ethoxyethane layer. Again, aqueous layer. Explanation, very straightforward. The density of water is greater than the density of ethoxyethane, so it forms the lower layer. Identify a piece of apparatus that should be used in step A to transfer 10 centimeter cube of the aqueous layer. Again, they're asking for exact value, which is why you're not using measuring cylinder, although it is fast and efficient. It's not accurate, but if you want it to be like very accurate, you use a volumetric pipette. Usually they have different labeled volumes, and you're specifically using 10 centimeter cube for this one. Triple I. Suggest why water is added to ethoxyethane layer in step 9 before the titration can take place. Okay, so the thing is, your NaOH, your sodium hydroxide, they don't really react or mix that well with your ethoxyethane. That's why you're adding like 10 centimeter cubes of water. This is so that your butanediol acid can transfer to the water first before the titration, so that there is going to be a reaction. Alright, next question. For a 2.81 gram sample of butanediol acid, the titer for the aqueous layer is 27.25 centimeter cube, and the titer for the ethoxyethane layer is 22.5 centimeter cube. The equation for the reaction between butanediol acid and sodium hydroxide is shown. Alright, so we can see the ratio is 2:1, and again we were given the concentration of NaOH in the earlier page. It is 0.5, so yeah, 0.5 times the volume, which is 27.25, but also make sure to convert it into decimeter cube and not leave it as centimeter cube. That's why you times it by 10 to the power of -3, or you divide it by 8,000, and you get the value, which is the mole of NaOH. And then after that, again, the mole ratio is 2:1, so you divide it by 2, you get 0.0068125. But you're not finished here either, because in the step 8 or like step 9, they basically said that you're only taking 10 centimeter cube, so that mole is for 10 centimeter cube, and in order to find the concentration, it has to be in decimeter cube, so that's why you divide it again by the volume. And with that, you obtain the concentration of butanediol acid of 0.68125 mole per decimeter cube. Alright, calculate the partition coefficient KPC. Again, it is given the equation, so I just snapped it from like the earlier section, so it's easier for you guys to see. Again, you can use the same method to find the concentration for ethoxyethane. Alright, you basically times it by the concentration, times it by the volume, you divide it by the molar ratio, and you again divide it by the volume so that it is in decimeter cube and not in 10 centimeter cube form. And with that, you have obtained the concentration of both ethoxyethane and your water. And basically, yeah, you divide it 0.1125 over, sorry, it's not water, it's butanediol acid, over 0.68125, and you obtain 0.165. So your KPC is 0.165 here. And this indicates that butanediol acid dissolves better in water because your KPC is less than 1. Alright, state why the student is only able to repeat the step 8 of the titration once. So let's go back to step 8. Alright, for step 8, you're transferring 10 centimeter cubes of your aqueous layer. Alright, why can you only transfer it once? Well, it is said in like the earlier part is that step 1, you only have 3 centimeter cube of distilled water in total using 10, and usually when you transfer something, you're not transferring like the whole thing entirely, because some like liquid might get stuck, some molecules might, not be transferred, whatever, something might happen, and it's just not possible for the transfer rate to like be 100%. So yeah, it is, again, the answer is fairly simple because it is not possible for all volume of the aqueous layer to be pipetted from the beaker, and that all volume refers to 30 centimeter cubes. Alright, suggest how you would modify the procedure to ensure the student can repeat the titration in step 8 more than once. It's very, very simple. You just, again, use a larger volume of water instead, higher than 30 centimeter cube. Alright, a different student forgets to shake the separating funnel in step 5 and describe the effect this would have on the calculated KPC value. This would again decrease. Why? Because if you're not like shaking it, perhaps the equilibrium has not yet been attained, has not yet been reached, and your butanediol acid may not have properly dissolved yet in your ethoxyethane. So the concentration would be lower, which also decreases the KPC value. Alright, next section, question 2, paper chromatography. So again, this paper has 3 questions instead of 2 questions. So yeah, they tend to be shorter and less intense. Okay, paper chromatography can be used to separate the individual amino acids formed when tripeptides are hydrolyzed. One molecule of a tripeptide produces 3 amino acid molecules, which are, by the way, colorless, so usually it might require you to spray some agent so that the spots are visible. Alright, a student is asked to identify the amino acids formed from the hydrolysis of 3 different tripeptides. We have A, B, and C. As you can see, 3 spots, 2 spots, and 3 very condensed spots with a lot of overlapping. Alright, figure 2.1 shows the result of the student's chromatography experiment. And the individual amino acids can be identified from their RF value. So they have very generously given the formula for your RF. So distance traveled by the amino acid spot over distance traveled by the solvent front. A. Suggest why each sample is applied to the chromatography paper using a thin capillary tube rather than a dropping pipette. So by the way, for thin capillary tube, the drops tend to be smaller. So you might have more control over it, might have more control over the drops. But for your dropping pipette, usually it's very large, no control, it's kind of difficult. So yeah, the purpose is basically so that samples can be dropped in a more controlled way or method. B. Suggest why it is necessary to spray a developing agent over the chromatography paper before the chromatogram can be analyzed. Again, this one has been mentioned earlier. Amino acids, they are colorless, and you intend to make the spots visible. So yeah, they are sprayed to make the spots become visible. Okay. Question C. Table 2.1 shows RF value for some amino acids in the solvent used in figure 2.1. Use the data in table 2.1 to identify the amino acids in tripeptide A. Again, you can use any point of the spot, but it's advisable to use the middle part. It doesn't have to be exactly in the middle, as long as it's close enough, because sometimes your calculated RF value won't be exact, and that's fine as long as it's close enough, difference by 0.01, 0.03, doesn't matter, same thing. Alright, okay, so with this you have 1 centimeter for spot A. That'll be 1/7, 14. Sorry, it's not 14, it's 0.14. That's my mistake. And then the second spot, 3.7/7, 0.53. And the third spot, the one on the very top, is 5.5/7, so it's 0.74. Use the data again. With this, we can compare the value 0.14, that is lysine. And do we have anything that is close to 0.53? We don't have an exact value of 0.53, but we do have a 0.5, so that would be your tryptophan. And for your third one, 5.5/7, 0.74, we don't have an exact value of 0.74, but we do have a 0.73, so that would be leucine. So those 3, tryptophan, lysine, and leucine. Alright, question D. Suggest why the hydrolyzed sample of B produces only 2 spots. Again, yeah, you can kind of guess already, if the amino acids are the same, they will be produced at the same spot. So 2 of the 3 amino acids are the same, that's why there's only 2 spots. Again, for question E, 2 of the spots from the hydrolyzed sample of C overlap. State the reason for the overlap. Again, they have nearly identical or similar RF values, and the RF values are very close to each other. That's why they tend to overlap. I suggest an improvement to the method that would allow the overlapping spots to be distinguished clearly. So for this, you can either change your stationary phase or your mobile phase. So you can use a longer chromatography paper or use a different solvent. It's totally up to you. It's only 1 mark. And you will want to use a different solvent because, again, different amino acids, different solubility. So yeah. Next question. I think that sums up for our chromatography. Alright, we have question 3, the final deal. Alright, so a scientist is asked to find the rate of decomposition of an aromatic diazonium compound and determine the order of the reaction with respect to the aromatic diazonium compound. A. The scientist is given 1.02 gram of an aromatic diazonium compound in a 50 centimeter cube beaker. Again, this is the classic 3-mark question. Usually 3 marks, very easy to obtain all of the marks. And you have to describe the steps the scientist should take to make a 100 centimeter cube standard solution containing 1.02 gram of this compound. Give the name and capacity of the apparatus the scientist should use. First things first, very standard, just like in the other paper, you would have to add distilled water to the beaker containing the compounds. And that beaker is the 50 centimeter cube beaker. Why are you adding water? You want to dissolve the compound. Next, transfer the solution and all of the washings. Make sure to answer solution and all of the washings, or like all of the rinses, because that one would give you 1 mark, right? And again, when you transfer something, usually not the whole thing is transferred, so you would want to mention that you also transfer the washings, because some of the liquid might get stuck here and there. And yeah, alright. Next, fill up the solution to the mark with distilled water and then shake well to mix the solution. So again, what exactly is the mark? Basically, in your volumetric flask, right, your 100 centimeter cube volumetric flask, they have a mark which indicates that it's a 100 centimeter cube. So you would usually try to fill it with distilled water if it's not filled all the way through, and then you shake it so that the solution is mixed well and not like the top is like very distilled and the bottom is more concentrated. We don't want that, so that's why you would want to shake it. Alright. Benzene diazonium chloride, an aromatic diazonium compound, decomposes in solution to produce phenol and nitrogen gas. The scientist warms 50 centimeter cubes of the solution to 50 degrees Celsius. The scientist records the volume of nitrogen gas produced at different times during the decomposition. I. Identify the piece of apparatus that should be used to maintain the temperature of the solution. Again, anytime you see maintain temperature, doesn't matter what kind of reaction, like 99% of the time, it's about using a thermostatically controlled water bath. Yeah, so that should be your default answer. And for II, here comes dependent variable. So this time around, they're asking for dependent instead of your independent variable. Again, dependent variable is what was changed due to the independent variable. And in the question, it is given they record the different volume of nitrogen gas produced. So the volume of nitrogen gas produced would be your dependent variable. III. Suggests why the scientist does not monitor the reaction by measuring the loss in mass. Again, not sure how you would be able to do both concurrently, like place the apparatus both in the thermostatically controlled water bath while also measuring the loss in mass. It's just not possible. You cannot weigh the apparatus when it is placed in the thermostatically controlled water bath. That's why you do not monitor it. Alright, so for question C, table 3.1 shows the result of the experiment. Okay, so for your volume, again, you just minus it, final minus VT. Again, this one, just make sure that you're actually calculating it correctly. The whole thing is only 1 mark and there's like so many sets of values. So yeah, II, plot a graph. Alright, the graph will come after this page, but we'll skip to IV. First, suggest one reason to explain the anomalous point you have circled. Assume no error was made in the measurement of volume. So this is likely due to timing error again, the classic question. Same thing as we have seen in paper 52 of Feb March 23. So yeah, it's usually like stopping or starting the timer either too early or too late. We'll see depending on the anomalous point. Alright. Okay, so for the graph, again, I'm using Keynote, so it is super duper difficult for me to draw a perfect curve. That's why it's very crooked, so I advise you to actually print it out. Don't do it digitally, but for the sake of this video, we will do it digitally and we'll work with what we have. Yeah, so, alright, okay, let's continue. So again, that is the value and you have to plot it with a cross, and alright, that would be the curve. It's not perfect, matter of fact it's far from perfect, and the one on the bottom would be your anomalous point. Now if we take a look at the anomalous point, it is lower than it should be, and if we take a look at the graph, like the trend, like the higher the time, the lower the V final minus VT, so likely the volume of nitrogen gas is recorded at a later time than it should be. So that would be the answer for your IV. Alright, okay. So again, make sure your curve actually hits all, if not nearly all, the points. And we'll go to question V. Use your graph to find the first two successive half-lives for this reaction. Alright, okay, half-life, self-explanatory. So the half of 57.2 is 28.6. Alright, so again, I have plotted it with the green dotted line. That'll be 28.6. It reaches the 9.75 mark. So 9.75 minutes. And then the second half-life, again, it's the second green dotted line. It's slightly on the bottom. It's at 21.25. So yeah, there's quite a bit of difference between my two values, but that is likely due to error of using Keynote and digital. Yeah, having drawn it digitally. So again, state the coordinates. So we have both the coordinates, the x and the y for both, and the half-life is 9.75 minutes. Second half-life, again, you just don't straight up take the 21.25 value. You have to minus it by the first half-life, and you have the half-life for the second one. So that is 11.5 minutes. Question VI. Use your answer to CV to state the order of reaction with respect to benzene diazonium chloride. Explain your answer. If you were unable to obtain an answer to CV, you may use values 8.6 minutes and 11 minutes for the half-lives. These are not the correct values. Again, as you can see, they're close enough to be considered as first. Alright, they're supposed to be the same, but due to error, yeah, they're a bit different. So the value of half-lives are constant and within the experimental error, and the order is first order. Alright, we have reached the end of this question and also the end of the paper. So again, I feel like this paper is less intense, right? Because it is divided into 3 sections instead of 2 sections, and it also feels like they are less wordy. And personally, I feel like this paper is easier compared to the other one because yeah, those are the things you would expect. They're not very difficult, not a lot of reading of instructions. That's actually my personal habit of not reading the instructions all the way through, but it is advisable for everyone to read the instructions from top to bottom before moving forward with the questions. Alright, this is a fairly short video because it's also a fairly short paper. That's it, and thank you for watching.